thank you. Good to be here. It's been a while since I've been here. It's a little bit of a ways from home, just a short 4.5 hour drive, but at least the time warp works in our favor going home. Coming east, it's always an hour extra. But I'll be talking today about lime and pH and a few things associated with it. For a forage guy, Chris did a real good job talking about the fertility aspect. I'm proud of him. Might buy my ice cream cone on the way home. But anyway, I am in Princeton, and Josh leaving in July. I get to come this way a little bit more, but I've worked over here through some agents with different projects through the years, and I always like getting back this way. So thanks for having me. So the first question is, why do we lime? Well, it's the basis to your soil fertility program. That is a foundational thing. If you can have a good liming program, a good soil pH, that goes a long way for your soil fertility program. And what we're doing is adjusting soil pH. And not all, 99.5% of the soil pH adjustments I'm dealing with, I'm going from a low pH to a higher pH. Every now and again, well, I've got a pH of 7.5 and I'm trying to grow blueberries. So that's a different thing, but we're usually trying to go up towards 7. And soil pH influences nutrient availability. I have a missile diagram to show like Chris did, root growth, and then herbicide activity. And you can limit your yield, not even realize it, kind of a hidden hunger type deal. So pH is a big deal and you get a big bang for your buck. Here's my missile diagram, and it basically shows the same thing as Chris's, but the wider those bars, the greater the plant availability of your nutrients. So if you look right there around 6.5, we're catching usually the fattest part of most of those bars. Well, kind of skinny right here for iron and manganese, but those are micronutrients. They're needed in small amounts. So we don't need a whole lot of iron to satisfy the plant needs. When we start shifting to the left, our availability, our bars get skinnier, but we get some things that come in here and get fatter. Aluminum and iron. When you have a low pH, you start tying up your phosphorus. So just keeping your pH right is going to make your phosphorus availability greater. And then another thing with aluminum, we say, well, low pH hurts your plant growth. That's true, but a big part of it is not necessarily the pH itself, rather the availability of aluminum. High aluminum availability will mess up the roots. Instead of getting a nice fibrous root system, you'll lose those really fine root hairs. You'll have shorter, fatter roots, and it's those real fine root hairs that are doing all the heavy lifting. So if you're losing these fine root hairs, you're not taking up as many of the nutrients. So yes, it is low pH, but it's really the aluminum causing you issues. This was a slide I got from Lloyd Murdoch. I started in 2010, and this work might have been done 20 years before that, but it's pretty neat. It demonstrates what I'm trying to say. Now, he had two bars, the top one dark blue and then the bottom one pink. The top one, they tried to maintain the pH at 6.6. Do I believe for 16 years they kept the pH at 6.6? No, but that was their target pH. And then they had another one at 6.2. So they're trying to have two distinct different soil pHs. And 6.2, that's not really that bad. I don't really get tore up if I see a field that has a pH of 6.2. But what they showed is adding 80 pounds of P2O5 every year. That's what's on this x-axis. And then our soil test P is on the y-axis. So as it goes from the bottom to the top, we have greater soil test phosphorus. So just, if you look at this, let's see, can y'all see the point? Okay, I'll quit walking in front of it. So right here, maybe 2 or 3 pounds difference in available or soil test phosphorus. As we go up in time, those those separations get a little bit wider. And after 16 years, again, applying the same amount every year, now we have a soil test phosphorus of 60 versus 74 or so. The only difference is pH. So keeping your pH right is going to make your nutrients more available. We applied the same amount, but some of it's tied up. Our soil test represents what's available to the plant or is an approximation thereof. So just simply watching your pH goes a long way. This was another slide I got from Murdoch. This was some work done at Lexington on some long-term plots. And what they did, they were liming. I don't know how many of you guys are familiar with research plots, but what we'll typically do, for me in row crops, I have a 10-foot wide plot that's anywhere from 30 to 50 foot long. And then like these tables here, I'll have a 5-foot break to separate my treatments. And then I have another set of treatments here. Well, they were applying lime to the treatments, but they weren't applying lime to the breaks between the treatments. After so long, they started noticing this grass. This is corn. What herbicides used with corn? Atrazine. The activity of that atrazine was not doing what it was supposed to do because of a low soil pH. So that's not really directly related to plant growth, you know, in the strictest sense, but it is because now you have competition. So just a simple, you know, maintaining your pH, I might get a little bit better herbicide activity. This is some work, did I miss one? No. This is some work that I did for my master's in the mid-90s. I went to the University of Tennessee at Knoxville, but my work was in Jackson, Tennessee and Western Tennessee. And my major advisor had set this up, and at the time when we started this, 14 years of the same treatments have been applied. So why am I showing you this? I want to show where most of the acidity in agricultural systems come from in the southeast U.S. So we have our nitrogen rate here, 0, 30, 60, 90, and this was in cotton. And then we had 2 tillage systems, no-till and tilled. And then within each of those, we either had no cover, which was just winter annual weeds, and then we had a vetch cover. Vetch is a legume. So most of our acidity in production row crop comes from nitrogen. You have nitrogen, and the predominant form, if you use urea, it's going to go to NH4. That NH4 ammonium form is going to nitrify and convert to NO3. So you have ammonium and nitrate. When it goes from ammonium to nitrate, it releases a hydrogen. Hydrogen's acidity. So nitrogen is what's driving our pH to drop in ag systems. So if we look here, as we go from 0 down to 90, in all these, our pH is dropping 6.2 to 5.4, 5.8 to 4.7, 6.3 to 5.4. That's because we're adding nitrogen. Well, if we compare the no cover to the vetch, this vetch is a legume. A legume makes nitrogen, 6.2, 5.8, 6.0, 5.4, 5.4, 4.7. So it really doesn't matter, oh, well, I'm producing organic nitrogen. It's better for the soil than urea nitrogen. Well, when we change the pH, that argument does not hold up. And then, I'm not saying it does in other ways. I'm just saying for pH, what we're talking about. But then, well, let's look at the difference between a tilled and a no-tilled system. Here we were sampling to 6 inches. Our sample scheme in Kentucky is to 4 inches. It's a little bit different in Tennessee. It's 6 inches regardless of the tillage. But what we see here is we have a little bit higher pH overall where we tilled it. And what we're doing is we're diluting that acidity more through the profile. Might be getting a little bit below that 6-inch depth. So we're mixing it. Does that matter? Well, yes, no, maybe. It just depends. But anyway, that's where your nitrogen, or that's where your acidity is coming from in most production systems. Okay, Now we've got soil acidity. We need to adjust it. How are we going to do it? We're going to do it with limestone. That's the most cost-effective, most common, easiest way to adjust acidity. By far, the most common form is calcitic limestone, followed by some sort of dolomitic limestone. I can't remember exactly what the ratio has to be to truly be considered dolomitic limestone, but dolomitic limestone is going to have a little magnesium in it. But what this reaction is, we have calcium and carbonate. There's our calcium carbonate, our limestone. Here's our acidity, 2 H pluses. Goes through a reaction. This right here, here's our H, water, carbon dioxide. Where did our acidity go? It went to form water and carbon dioxide. There is our acidity. We have taken that hydrogen out of solution. It is now water. Our pH is going to go up because we removed the hydrogen that is being measured by that pH electrode. Quicklime. Don't really use this in ag settings. It's hard to deal with, but it's an oxide. So now for every oxygen, we can consume 2 hydrogen. It's going to form water as well. Hydrated lime. Same principle. We're making water with the addition of a hydrogen. Pelletized lime, that's just a fancy form, a processed form of calcitic limestone. And then we have some waste products. Well, seashells, that was one of the first items ever used to neutralize soil acidity. It has carbonates in it. Paper waste and biosolids. Some people think, oh, well, biosolids, that's just poop. But the thing about it, some of them are lime stabilized with calcium oxide. What they do, they treat them with this, raise the pH to 12, and they do some other things. But what they're doing when they raise that pH real high is killing a lot of the bad things associated with waste. It's killing the bad bugs. Well, when you get done with that, you have a little bit of nitrogen, hardly any potassium, and then a little bit of phosphorus, and you have some sort of liming activity. My parents lived near McMinnville, Tennessee. There's a lot of nursery production down there, and there was actually a lawsuit one farmer filed with the county because he wasn't getting access to the biosolids. It was all going to one person. That was a free product they were giving away. He was making the best of it. He was spreading on his land. Someone found out about it and said, I want it. It's like, nope, I got the contract, sorry. So there was actually a lawsuit because they couldn't get the stuff. So that's something else. If you take nothing else home today from my talk, please take home this next part. It is not calcium, it is the carbonate, oxide, hydroxide that is reducing your acidity. We have gypsum here, calcium sulfate. I've put out that nice little reaction. There's my hydrogen, here's my hydrogen at the end. Calcium is not really involved with the acid neutralizing reaction. It just happens to be there when it's going on. So what's going on here? Does anyone know what would happen if I take this hydrogen and mix with sulfate, H2SO4? Anyone know what that is? Sulfuric acid. So if I'm taking calcium sulfate and by some reason I can make it form sulfuric acid, what's going to happen? It's going to dissociate. By definition, acid, a strong acid, is going to release a hydrogen. So let's just say, okay, yeah, that sulfate did grab a hydrogen for a millisecond. Well, it quickly reduced it because it's a strong acid. Okay, calcium chloride. What's H plus Cl? Hydrochloric acid. What's going to happen there? The same thing. We're not going to consume any hydrogen for any amount of time and increase our pH. So it's not the calcium, it's not the calcium. It's the carbonate, oxides, hydroxides. Anything that can consume a hydrogen and end up with the end product of water. So that's really important. A lot of people think, oh, it's the calcium. It's like I had a friend in high school. He had white. I had a friend in college. He said he went white when he was a freshman, white-headed when he was a freshman in high school. So a lot of times you think, oh, white hair means, well, they got a few years on them. A lot of times that's true. But that's the same thing with this calcium. Just because, oh, it's always associated with my Lyme, that means that's what's doing it. That's not the case. White hair doesn't always mean you got some years to you. So just remember, it's the oxide, hydroxide, and carbonate. Couple misconceptions. I hear this a lot. I was in Knoxville in the mid-90s, and they were talking about this then. Pelletized lime is much better and much faster reacting than ag lime. Well, I can spread half as much or a quarter as much and get twice the change in half the time. No, it's based on your relative neutralizing value. A pound of lime is a pound of lime. Liquid lime is much better than ag lime. There's not much of this, but there is a true liquid lime product. You take real fine ground up calcium carbonate, you put in a little bit of clay, and then put about 50% water, and then that clay is going to suspend the calcium carbonate in the water, and you spray it. Well, it still comes down to what your R&V is. R&V of 10 of this is going to be an R&V of 10 of this. And then high magnesium lime causes compaction. I've heard a lot of different things, and we'll kind of touch on these. I'm not going to touch on this per se anymore, but there's something else that's being promoted as liquid lime, and we'll end up the talk with that. So pelletized lime, it is a high quality product. They're usually using good rock. It has a real fine grind on it. Then they're going to take it through a process, add some binders, put it into a pellet, sometimes put it into a bag, and move it to wherever it goes. It is a high quality product. But anytime you add any step to any process, it costs money. So they take this high quality lime from the quarry, they truck it somewhere to do an operation. Usually they're going to make sure it's got a fine enough grind, so they might have to regrind it. Then they're going to have to add some sort of binder, which comes with a cost, and then they're going to have to make a pellet, which also comes with a cost, and then they're going to either put it in a bag or put it somewhere else and then ship it somewhere else. Most of your ag lime goes from the quarry to the farm that they're spreading, and it's spread. So you got a lot of extra steps, a lot of extra processes that adds cost to that product. Last time I checked, per ton, ag lime around Princeton was about $15 or $17 a ton. High quality pelletized lime was running about $300 per ton. A lot of difference there. Am I going to call a lime truck and have him spread lime on my half-acre yard? Nope. I'm going to put pelletized lime down. But if I'm spreading 100 acres, I'm going to use ag lime because it's more effective and not more effective, as effective and a lot cheaper. So it has many fines and it has a higher CCE, calcium carbonate equivalent, then it's faster. Not really any faster, but it's going to be more pure usually. They're going to use the best of the best. So, you're buying a high quality product. It will generally take less pelletized lime than ag lime just because you have a higher quality product. But it's not going to be half as much. Or somewhere around a 67 R&V is about a state average for Kentucky. If you get pelletized lime with the R&V of 90, that's not a whole lot of difference. So, 25% better. Well, not even that. But $15 versus $300. It's going to have to be a lot better to pencil out. Yeah, that's one we'll talk about for that. We'll move on. This calcium-magnesium ratio, it's pops up 2 or 3 times every year. Um, and there's some truth here. Most of these things have some thread of truth associated with where these kind of statements, these theories come from. But high levels of magnesium can cause dispersion. Okay, let's go with that. And let's just say that's true, which it is. I can do that in the lab. Now, what we're thinking, we have soil particles that are dispersed. So what is happening, you have magnesium in your soil, enough magnesium, and you can't do it with lime, but if we have enough magnesium, they don't allow those soil particles to get too close because they're both positive charges, like taking 2 refrigerator magnets and try to make them stick together. They're only going to get so close before they start repelling each other. So you have you have dingy water versus a flocculated soil where they're clumped together, and then you'll have the flocculated water, clear water, and dirt at the bottom dispersed. You'll have dirty water all the way through. So when that water goes through the small pores, it's going to settle out. We're depositing small soil particles in these soil pores. Well, that's the theory behind that. Anytime you increase the density per given volume, that is, in the truest sense of the word, compaction. Well, I said all this stuff can happen. It's not going to happen in your field for these 3 reasons down here. One, we're not going to find near enough magnesium to do this in a real soil situation. I can go into the soil chemistry lab, get pure magnesium carbonate, and add enough of that. But you're never going to get the right ratio of magnesium to calcium from a lime. If you did, magnesium is going to leach out faster than calcium, so it's going to be more transient. It's not going to do much. And then an acre furrow slice is 2 million pounds of soil. Let's just say we add a huge rate, 10 tons of lime, it's still just 1%. You're not really making enough difference to make a difference. I said you'll never find the right magnesium. Well, let me go to this one and I'll back up. Here's a slide that Frank Secor made. We gave a talk several years ago. And what we have, 99.3% of the Kentucky soils have a calcium-magnesium ratio greater than 75 to 25. So 3 times more calcium than magnesium. To get this dispersion to occur, right here, can you see this looks pretty clear, this looks pretty dingy. We have to have twice as much magnesium as we have calcium just to get where we start making our soil dingy. Oops, wrong way. Now, these are some limes, this is some quarries from around Kentucky. The top 2 are from Princeton. Here's my calcium percentage, 36 to 1.6. So I've got about 25 times more calcium than I do magnesium. 38 to 1.1. 35, 36%, or 36 times more calcium than magnesium. Here's one in Bourbon County. It's got 3% magnesium, but I still have 34%, 10 times more calcium than magnesium. Remember, for that dispersion to occur, I've got to have at least twice as much magnesium as I do calcium. Does that make sense? Even though I can go into my soil chemistry lab and start adding stuff and make that happen, I can make this soil disperse, we're never going to do that in an agricultural setting. So yeah, there's some basis too. Well, if I have too much magnesium, I can cause compaction. Very true. You're not going to be able to afford to do that because analytical grade magnesium carbonate is going to cost about $100 a pound. That's really expensive lime. So anyway, Is there any questions about that before I move on? I think that might be the second most important part of my talk. So how do we determine lime rate? Well, Chris gave, again, I'm proud of him. He gave a very good explanation of how to take a soil sample. We want a good soil sample. We want that soil sample to represent the area that we want to fertilize or lime. So we take a good soil sample, we send it to the lab, we get results back. Then it depends on what crop we're trying to grow. It depends on our pH, our water or salt pH, and then our buffer pH. And what we use, I say in Kentucky, what the University, of Kentucky uses is the Socorro buffer. You put it into the water pH, you just mix a certain amount of water with a certain amount of soil, stick an electrode in there, and it gives you a number. We actually at UK use a salt pH, which tries to overwhelm some of the fertilizer salts. If you have a dry fall, you get a little bit of fluctuation, a false low reading because of these fertilizer salts. So everyone, including myself, is used to seeing a water pH. We do a salt pH, convert it back. What you see is a water pH. Don't want to confuse you on that. The pH you're used to seeing is the same pH you're doing. We're just measuring it a little bit differently, reporting it as this. But it measures the active acidity. Once we do that, then we put some of this Socorro buffer in on top of it, stir it again, and measure the pH again. So the pH starts out at 7.5, and however much residual acidity or reserve acidity is present will influence how far our pH drops, and that gives us an indication of our residual or reserve acidity. So we use this plus this to come up with a lime rate. What our active acidity is, we have a 12-ounce Pepsi bottle or can, and we measure that. Well, that's all we know is what that is. But when we're measuring our residual acidity, that tells us how much we have in reserve that's going to fill up this when we neutralize it with limestone. So we don't know if it's a 10-ounce bottle or it might be a 15-gallon bottle. So this residual or reserve acidity is telling us how much we really have to neutralize to make a difference. That buffer pH does it for us. What influences our limestone rates? Well, the crop that we're growing. What target pH are we shooting for? The amount of acidity present, the amount of reserve acidity. Well, what influences our reserve acidity? The amount, and to a lesser extent, the type of clay, and the amount of organic matter. More or less your cation exchange capacity. But we get that from that buffer test. And then our limestone rate is influenced by the quality of our limestone, our RNV, relative neutralizing value. 90+% of what I work with, we're shooting for a target pH of 6.4. That's pretty much everything but tobacco and alfalfa. Alfalfa is 6.8, tobacco a little bit higher or lower at 6.6. In Tennessee, and it's not really wrong, actually it's a number I use a lot of times, shoot for 6.5 and you're going to be good most of the time. Alfalfa has a higher demand for molybdenum, and I believe that's why I've never had anyone give me an answer for why we did that, but I'm pretty sure we jack up our pH just a little bit higher for that. Is there another reason? Would it be?
That's what Ken Wells used to say.
I wish I would have talked to Ken. So there we go. It is for molybdenum availability. Surface applied lime. When we're talking about hay fields, pastures, generally, unless you're renovating and doing some tillage, we're talking about surface applications. Grove and Blevins, Grove was, I don't know, he's been around here, 40 years now? He's still hanging around and doing good stuff, but back in the late 80s, they found unless your pH was really below 4.5 or 5, surface applied lime is just fine. And really, you don't want to see a pH of 4.5. You've or someone has neglected that land for a little bit too long. My research showed something pretty similar, about 4.8. But again, you shouldn't really get in that situation. And I told you earlier, the second slide with my missile diagram, that exchangeable aluminum is the problem, not necessarily low pH. It's the exchangeable aluminum messing the root growth up. Within 1 year, I I had my pH of 4.8. Within 1 year of lime application, there was no exchangeable aluminum left. My pH only went up a little bit, but I got rid of the stuff that was really causing trouble. So it's really pretty effective. Most of your acidity and no-till is at the soil surface because that's where you're applying your nitrogen. So apply your lime, neutralize that acidity. Here's the same thing I showed you before after 14 years. And then we applied the recommended rate of lime to each individual plot. So we had, let me back up here, 6.2 to 5.4, 6.6 to 6.3. We're shooting for a target pH of 6.5. Before they started using this buffer, this was the Adams-Evans buffer developed in Georgia, what they were doing, their recommendation was 3 tons of lime to get a 1 ton change in pH. Well, that was giving them guidance, but not near as much as this, because you don't know what kind of CEC, what kind of clay you had. This gave you a better estimate of how much lime, or how much lime needed to be added to neutralize the acidity. The vetch from 5.8 to 4.7, we never really got quite there with that 5.3. But if we look in that same situation where we tilled it, we did. So that's where that statement said, unless you get really below 4.5, 5, surface application of lime is going to be okay. But would I ever say, yeah, pH is pretty low, I think you should do deep tillage to incorporate your lime? I wouldn't recommend getting out of a no-till system to do that. If you're going to use tillage to do another establishment of a crop, that is the time to do it, but I wouldn't recommend doing it just to incorporate. Real quick, just surface area is the key on reactivity. If we take a 1-inch block of limestone and we cleave it 2 ways, so we have a surface area of 6 square inches with that 1-inch cube. We cleave it 2 ways, now it went to 24 inches. We keep slicing it and slicing it and slicing it, our surface area grows exponentially. So 1 cubic inch of limestone, if it passes a 100 mesh screen, is 60,000 square inches of surface area. The finer that stuff is, the quicker it reacts. So just taking the same block of lime, this is the gravel you put in your driveway, this is the stuff that neutralizes acidity. It is able to be broken down because it's in contact with the soil. So our R and V, relative neutralizing value, 3 numbers. Our calcium carbonate equivalent, that's the purity, how good is that rock? The fineness. We say if it's passing a 50 mesh screen, 50 mesh means there's 50 holes per linear inch. That's pretty small. So 50 holes per linear inch, all that is 100% effective in our calculation. If it passes the 10 mesh, but not to 50, we say half of that's effective. So 100% of that plus half of this plus this. And that's how we calculate our relative neutralizing value. That's putting everything on an even playing field. How do you apply 100 pounds of nitrogen using urea versus ammonium nitrate? Well, urea is 46% nitrogen, so 100 pounds, I need to add about 220 pounds of urea. If I want to add 100 pounds of ammonium or nitrogen is ammonium nitrate, need to use a little bit more, right? Because it's less pure. This is just straight from AGR1. When you get your soil test back, they run it through a computer program, but here's the math behind it. Takes your water pH, your buffer pH, your target pH, and gives you a rate. So 2 tons of lime per acre based on this. We're going to say my lime has a 67% relative neutralizing value, just like calculating my nitrogen rate with urea versus ammonium nitrate. I divide by the percentage of purity or the actual nutrient. So 2 tons divided by 0.67, my actual rate to get 2 tons of effective lime is 3 tons of that limestone. If my RNV was 50, now I have to add 4 tons. If my RNV was 100, I add 2 tons. Just simple conversion. Here's some good online calculators. This top one, it just crunches numbers for you. I mean, that's good. You can, your soil test gives you that. This one's really pretty useful. It can compare lime rate by RNV, and you can include hauling and spreading fees for 3 sources. So if I have 3 sources or, not too far away, or just 3 sources, period, I can plug them in there. It costs me however much per ton, how much to haul, how much to spread, and they'll tell you which is the best value. Just because it's a little bit more pure, if you have to haul it twice as far for the same cost or a little bit more cost, it might not be the most effective or the most economic. And then each year in the spring and in the fall, the regulatory services goes out and pulls samples from all the quarries that are selling limestone, and then they post them. You can go to Division of Regulatory Services, just type in University of Kentucky Regulatory Services and push some buttons and you'll finally get to here. And here's the results for the fall of 22. The spring of 23 will be coming out probably sometime March. And maybe February. It'll allow you to do this. That's good information. Oh, when did it? Yeah. That was in September, so probably about March. Again, this is what it tells you, your calcium carbonate, your purity, and then, I really don't look at calcium versus magnesium. This is what I look at, where I can get it and what my RNV is. But I do want to make a point here. I said it's your purity and your fineness. This rock right here, it's 98% CCE. That's pretty pure. But look at my R&V, it's 50%. What's the difference between this ag lime at 98% CE versus this ag lime at 98%? The grind. 96% past the 10%, only 74. 64% of this passed my number 50 sieve, whereas only 27%. So look at that number. That makes a big difference. This is a study I had a few people help me out this end of the state with. We were getting questions about this product. Liquid lime is what it was called. It was actually calcium chloride. Someone said, hey, will you help me set out an experiment? I keep getting questions about this. I'd like to do it in my county. And that person might or might not be in this room at this moment. But anyway, we did. I said, you know what, that's a great idea. Let's see how many agents would be willing to work with us on this. We can get a pretty wide data set. So what we did, we started in the spring of 21 and had multiple locations. Ended up with 15 or 16. I think 10 minutes. Okay, good deal. I think it was actually 15, but we had a 5x5 plot, and then we had a lab trial where we did concurrently with 4 ounce, what you go to the doctor and pee in the cup in. We put dirt in there and mixed it with lime and then incubated it, kept it in the room, in a enclosed room until December 10th, and then it was no longer enclosed. But we got some good data. Our treatments for both of these studies were a check. We didn't apply anything. We had the advanced cow product at 5 gallons per acre, pelletized lime at 2 tons per acre, adjusted for the R and V, and then ag lime at 2 tons per acre, adjusted. And instead of trying to take a soil pH from all locations and send out, well, you need 2.5 tons, you need 3 tons, we just sent out the same thing and to everybody, and then they applied it. So we weren't we were not following our recommendations, but we were seeing what's going to happen when you apply the same amount of these products to a soil. So you can see, we had some in western Kentucky, south, the central part, and then some out here. So that's not a bad representation of the state. Before we did anything, we collected soil samples, had agents send me a soil sample. We were trying to get pHs below 6, something that should respond to lime. And then we sent them the product, and then they laid out their plots. There were 3 replications, 4 treatments, so 12 plots in a given area. We collected soil samples from each plot to 4 inches, and then spread the products. And then we collected soil samples and tissue samples about 3 months later after that next cutting, and then biomass. And then we came back and collected soil samples roughly a year afterwards. Here's our data. We had our soil pH, this is from the field study. Initial pH was roughly 5.7, 5.7, 5.7, 5.8, 5.8, 5.8. So 5.8 when you average them across all 15 locations. 3 months out, adding nothing, it was about the same. Adding liquid calcium, about the same. Adding pelletized lime, it'd gone up just a little bit. And ag lime, it went up a little bit. You can see we have 2 groups. These letters mean they're statistically, scientifically, not different from each other. So the check and the liquid calcium were scientifically or statistically the same. The pelletized lime and ag lime after 3 months were statistically the same. About a year out, these 2 were still grouped together. 5.9, 5.8, 5.8, 5.8. Really didn't change in the year. We didn't add anything, and we added liquid calcium chloride. Remember, the chloride's not going to consume hydrogen. Then we added, or not added, a year out, our pelletized lime and our ag lime, about 6.5. So it went from 5.8 to 6.5. These were the same, these were the same. Looking at this exact same data a different way, it was about the backwards a little bit, forwards a little bit, forwards a little bit, forwards quite a bit. So we did make a difference by adding the calcium carbonate. We didn't make a difference adding the calcium chloride or nothing. Well, here's our lab study. We started with a soil that had an initial pH of 5.2, pulled that out of the farm, ran the pH, mixed it in a cement mixer, so we got a good representative sample, applied those same rates to a 4-inch cup, kept it at ideal conditions. We added moisture twice a week by weight, kept it inside and room temperature. 1 month out, our check and our liquid calcium, 5.2, pelletized lime and ag lime, about 6. 3 months out, 5, 6.5, or 6.2, 6.3. 6 months out, 5, 6.5. We're getting a change in pH. Well, right about here, about month 5.5 is when the tornado hit. We were able to recover most of those samples. I brought them home, put them in my garage. So this one too, they were not in the same conditions here, but still, 5.2, 5.1, 5. This is a year out. 5.6 or 5.9, 6.1, 6.3. We're changing. That was my 45-minute mark, and I'm almost done. So that lab study and this field study support each other. And it wasn't like I split a field in half and I did this, I did this. We replicated it and randomized it within each field. Well, if it doesn't change pH, maybe something else. Grass people care about dry matter. That's what you're selling. That's what you're feeding your cattle. No differences here. Protein, ADF, NDF, TDN, these things mean something to you, probably a lot more than me. But what I can tell you is it doesn't matter what it is, they're all the same statistically. So there was no difference in any of this stuff. Just real quick, so there is actually a relative neutralizing value with this advanced cal. They say it is, where is it? R and V of 0.045. There is a little bit of free calcium carbonate in there. So we're going to compare R and V of 67 to R and V of 0.45. Doing all the math, we want a 2 ton per rate with ag lime using our 67 R and V, 3 tons. I showed you that before. Using advanced cal, 0.45 R and V, we need to add 444 tons to get the same change as we get with this 3 ton rate. Well, per acre. Yeah, 444 tons. If you do the math, that works out to about 79,000 gallons or equivalent to a 3-inch rain. That's a lot of a product to put down. Their use rate is 2 to 5 gallons per acre. And it was funny, the kid that started this, summer intern, he's like, you ever check the pH of this stuff? I said, no, that's a good thing for you to do. He sticks the pH probe in the jug, and it's 4.5. Simple math. It's hard to go from 4.5 to 6.5 if you have a pH of 5.5. Those averages don't work. And Chris bought this for us, and we only bought, the small 2.5 gallon jugs, but that was $30 per gallon. So more or less, I'm wrapping it up. pH is really important. It's one of the cheapest amendments you can add. Compare the cost per R&V, not the cost per ton. And watch these things that are too good to be true are really too good to be true. If you have any questions about things, this NCERA 103 website, there's a lot of products we never test, but there's people that do. A lot of that stuff is posted here. So I've probably used up all my time. Maybe answer a question or two while Chris is getting Greg mic'd up. Any questions or comments? Yes. my thing was applying liquid calcium was almost as good as applying nothing. But if you applied the water at the right time, like in a drought, you'd probably get some sort of benefit. But yes. Yes, sir.